Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should make your brain gently buzz with profound strangeness. Imagine a place in the universe where the very fabric of reality, space itself, and time along with it, is so profoundly warped, so impossibly bent, that nothing, not even light, can escape its grip. We call these phenomena black holes, and the name itself is a fantastic misnomer. They aren't holes in the conventional sense, not cosmic voids or tunnels to another dimension. Instead, they are the ultimate expression of gravity, objects so incredibly dense that they challenge our most fundamental intuitions about matter, energy, and the very nature of existence. Think about it. Light, the fastest thing in the universe, travelling at an astonishing 299,792,458 meters per second. That's fast enough to circle the Earth more than 7 times in a single second. Yet a black hole is a cosmic trap from which even this ultimate speedster cannot flee. It's not that the light runs out of energy or gets sucked in a simplistic way. It's far more profound. The space itself within a certain boundary around a black hole is falling inward faster than light can travel outward. It's like trying to swim upstream against a current that's moving faster than you can paddle. No matter how hard you try, you're inevitably pulled further into the current. This isn't just mind-bending, it's a direct consequence of Einstein's theory of general relativity, a theory that revealed gravity isn't a force pulling things together, but a curvature in the very geometry of space-time caused by mass and energy. Black holes are where this curvature becomes so extreme that it creates an inescapable cosmic abyss, not of emptiness, but of concentrated space-time distortion. They are the universe's ultimate cosmic drain, not because they suck things in, but because they are the ultimate end state of gravitational collapse. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over their world at all hours of the day and night, connecting us through the shared marvel of the cosmos. Let's start with a thought experiment that makes the concept of a black hole a little more tangible, even if the reality remains profoundly abstract. Imagine our Earth, a familiar planet rotating gently beneath you. It has a mass of about 5.97 times 10 to the 24th kilograms and a radius of roughly 6,371 kilometers. Now let's play a cosmic game of compression. What if we started to squeeze the Earth? Not just a little, but relentlessly, until all that incredible mass was packed into an impossibly small volume. If you could compress the entire Earth down to the size of a marble, a tiny sphere just a centimetre or so in diameter, that's when things would get truly bizarre. At that point, the gravitational pull at its surface would be so immense that nothing, not even light, could escape. The Earth, as we know it, would become a black hole. This isn't just a fun hypothetical, it's the core idea behind what a black hole is. Not a void, but an object of extreme density, where gravity has won the ultimate victory. To truly grasp this, we need to take a gentle step back and revisit gravity itself. For centuries, we understood gravity through the brilliant insights of Isaac Newton. He described gravity as a force, an invisible pull between any two objects with mass. The more massive the objects, the stronger the pull. The closer they are, the stronger the pull. This explained why apples fall from trees and why planets orbit the sun with incredible accuracy. Newton's law of universal gravitation was revolutionary, describing how gravity works with stunning precision. But it didn't explain why. It didn't tell us what gravity is at a fundamental level. That deeper understanding came with Albert Einstein's theory of general relativity, published in 1915. Einstein didn't just refine Newton, he completely reimagined gravity. He proposed that mass and energy warp the very fabric of space-time, much like a bowling ball placed on a stretched rubber sheet creates a dip. This dip, this curvature in space-time, is what we perceive as gravity. Objects don't pull on each other. Instead, they follow the curves in space-time created by other massive objects. The Earth orbits the Sun not because the Sun is pulling it with an invisible rope, but because the Sun's immense mass has created a deep well in space-time, and the Earth is simply following the curvature of that well. This is a profound shift in perspective, moving from a quote 3 to a quote 4. Now, let's connect this geometry back to our cosmic drain. Every object with mass has an escape velocity, the minimum speed an object needs to break free from its gravitational pull and travel into space, never to return. For Earth, the escape velocity is about 11.2 kilometers per second, or about 25,000 miles per hour. That's why rockets need powerful engines to get into orbit or travel to other planets. For the Moon, it's lower. For Jupiter, it's much higher. This concept of escape velocity is crucial because it sets the stage for the most defining feature of a black hole. What happens when an object becomes so incredibly dense, so concentrated in its mass, that its escape velocity exceeds the speed of light? The speed of light, as we discussed, is the ultimate cosmic speed limit. Nothing with mass can ever reach it, and light itself always travels at it. If the escape velocity of an object surpasses this universal speed limit, then not even light can get away. It would be trapped, destined to fall back inward. This is precisely what defines a black hole. The boundary beyond which nothing, not even light, can escape is called the event horizon. It's not a physical surface you could stand on, but a conceptual boundary in space-time. It's the point of no return. Imagine a river. If you're in a boat and the river is flowing slowly, you can easily paddle upstream. That's like trying to escape a planet with a relatively low escape velocity. But what if the river starts flowing faster and faster? At some point, the current might become so strong that even if you paddle with all your might, you're not making any progress upstream. You're just holding your position relative to the banks. And if the current flows even faster, faster than you can paddle, you'll be carried downstream no matter how hard you try. The event horizon is precisely that point where the flow of space-time into the black hole is faster than the speed of light. Anything that crosses that boundary, whether it's a particle, a spaceship, or a photon of light, is irrevocably drawn inward. It's the ultimate one-way trip. Inside the event horizon, all paths lead to the center, and at that very center, according to general relativity, lies something even more astonishing: the singularity. This is a point of infinite density, where all the mass of the black hole is compressed into an infinitesimally small volume. Our current understanding of physics completely breaks down at the singularity. It's a place where the laws of physics, as we know them, cease to apply, and space-time itself is stretched to an infinite degree. It's a place of ultimate mystery, hidden from our direct observation by the impenetrable veil of the event horizon. We can never see the singularity, only infer its existence from the effects of the black hole's immense gravity. This concept of an event horizon and a singularity fundamentally changes our understanding of the universe. It means that gravity, in its most extreme form, can create regions of space-time that are utterly disconnected from our observable universe. Once something crosses that horizon, it's gone forever, not just from our sight, but from our causal universe. This isn't just a matter of strong gravity, it's a complete reshaping of the space-time around it, a cosmic maelstrom that defies our everyday intuition. And the deeper we delve into these fascinating objects, the more we realize how much we still have to learn about the most extreme environments the cosmos has to offer. We stand at the precipice of understanding, having glimpsed the ultimate mystery of the singularity, that unfathomable point where our physics falters, where density becomes infinite, and time and space as we know them cease to hold meaning. It's a concept that stretches the very fabric of our imagination. But as profound as the singularity is, it begs an even more fundamental question. How do these cosmic behemoths, these space-time distortions, even come to be? How does such an extreme object form in the first place? To answer that, we must turn our gaze to the lives and deaths of stars, those magnificent cosmic furnaces that paint our night sky. Imagine, if you will, the birth of a star. It begins as a vast cloud of gas and dust, slowly collapsing under its own gravity. As the cloud shrinks, the pressure and temperature at its core skyrocket, until, eventually, nuclear fusion ignites. Hydrogen atoms fuse to form helium, releasing an immense amount of energy. This outward pressure from fusion perfectly counteracts the inward pull of gravity, creating a delicate cosmic ballet that keeps the star stable for millions, or even billions, of years. Our own sun is a perfect example of this celestial balancing act. But even stars, for all their brilliance and power, are not immortal. They have life cycles, just like everything else in the universe. What happens when a star runs out of its nuclear fuel? For stars like our sun, the process is relatively gentle. They swell into red giants, shed their outer layers, and eventually settle down as white dwarfs, dense, Earth-sized embers that slowly cool over eons. However, the story takes a dramatic, even violent turn for stars that are truly massive. We're talking about stars that are at least 8 to 10 times more massive than our sun. These stellar giants burn through their fuel at an astonishing rate, living fast and dying young. When their core runs out of lighter elements to fuse, gravity, relentless and unforgiving, finally wins the battle against the dwindling outward pressure. The core collapses in on itself with terrifying speed and force. In a mere fraction of a second, it implodes, reaching densities so extreme that protons and electrons are crushed together to form neutrons. This catastrophic collapse then rebounds, triggering a colossal explosion that rips through the star's outer layers, blasting them into space with unimaginable energy. This is what we call a supernova, a cosmic firework display so bright it can briefly outshine an entire galaxy, It's one of the most powerful events in the universe, a spectacular, yet sombre, farewell from a dying star. What's left behind after such a cataclysm depends entirely on the mass of the original star's core. If the remnant core is between about 1.4 and 3 times the mass of our Sun, it typically forms a neutron star, an incredibly dense object where a teaspoon of its matter would weigh billions of tons. Neutron stars are fascinating in their own right, essentially giant atomic nuclei, spinning rapidly and often emitting powerful beams of radiation. But if the core left behind after the supernova is even more massive, if it exceeds roughly 3 times the mass of our Sun, a threshold known as the Tolman-Oppenheimer-Volkoff limit, then even the immense pressure of degenerate neutrons isn't enough to halt gravity's relentless grip. The collapse continues, past the point of a neutron star, past anything we can truly comprehend, until all that remains is an object so dense, so compact that it warps space-time beyond all recognition. This, my friends, is the birth of a stellar mass black hole. It's the ultimate cosmic implosion, a point of no return forged in the crucible of a dying star. These stellar mass black holes, born from the spectacular death throes of giant stars, are just one kind of black hole we've discovered. The universe, in its infinite creativity, has conjured up a few different varieties. Beyond the stellar mass black holes, which typically range from a few to tens of solar masses, we encounter the true titans of the cosmos, supermassive black holes. These are the leviathans weighing in at hundreds of thousands to billions of times the mass of our Sun. We find them nestled at the very hearts of most, if not all, large galaxies, including our own Milky Way, which hosts Sagittarius A star, pronounced quote 7, at its core. How do these colossal beasts form? That's a question still actively debated by astronomers. We believe they grow over cosmic timescales, perhaps starting as smaller black holes and accumulating vast amounts of gas and dust, or merging with other black holes during galactic collisions. Imagine the sheer gravitational power required to hold a galaxy together, and you begin to grasp the scale of a supermassive black hole. Then there's an intriguing category, still somewhat elusive, called intermediate mass black holes, IMBHS. These would fall in between stellar mass and supermassive black holes, with masses ranging from 100 to 100,000 times that of the Sun. Evidence for them is growing, often found in dense star clusters, and they might represent a crucial stepping stone in the formation of their supermassive cousins. The universe, it seems, enjoys a spectrum of gravitational monsters, so we understand how they form. But what happens around a black hole? What are the observable effects of these invisible cosmic entities? This is where the story gets even more mind-bending, where the extreme physics of black holes truly manifest. Imagine for a moment an unfortunate astronaut, or perhaps just a very curious space probe, venturing too close to a stellar mass black hole. As it approaches, the gravitational pull becomes incredibly strong, but it's not uniform. The part of the object closer to the black hole experiences a significantly stronger gravitational force than the part farther away. This differential gravity creates an intense stretching effect. If you were falling feet first, your feet would be pulled much harder than your head. This immense tidal force would literally stretch you out, elongating your body like a piece of cosmic taffy, until you're a long, thin strand of atoms. We call this chilling phenomenon spaghettification. It's a gruesome yet fascinating testament to the extreme gradients of gravity near a black hole. For supermassive black holes, the tidal forces at the event horizon are actually weaker because their event horizon is much larger, meaning the gravitational gradient is less steep across a typical human body. So, you might cross the event horizon of a supermassive black hole without even realizing it, only to face the inevitable journey to the singularity within. But black holes aren't just cosmic shredders, they're also incredibly dynamic engines that can profoundly influence their surroundings. Picture a cosmic drain, a super powerful whirlpool in space. When gas, dust, or even entire stars get too close to a black hole, they don't just fall straight in. Instead, they often get caught in its gravitational embrace, spiraling inward. As this matter orbits the black hole, it forms a rapidly rotating, flattened structure called an accretion disk. Think of it like water swirling down a drain, but on an epic astronomical scale. The particles within the accretion disk rub against each other due to friction, heating up to incredible temperatures, millions of degrees Celsius. This superheated plasma glows intensely, emitting vast amounts of radiation, particularly in the X-ray spectrum. So, while the black hole itself is invisible, the accretion disk surrounding it shines with a fierce, brilliant light, making it one of the most luminous objects in the universe. It's a dramatic cosmic beacon, powered by the insatiable hunger of the black hole. And the show doesn't stop there. For some black holes, particularly supermassive ones with active accretion disks, not all the matter falls in. A small fraction of the superheated plasma can be channeled by powerful magnetic fields, launching it away from the black hole's poles in incredibly fast collimated beams called relativistic jets. These jets, travelling at nearly the speed of light, can extend for hundreds of thousands of light years into space, blasting through galaxies and intergalactic medium. They're like cosmic geysers, beacons of immense power that reveal the presence of the hidden black hole at their core. So, here's the ultimate paradox. Black holes are black. They absorb all light, making them impossible to see directly. Yet we've gathered overwhelming evidence for their existence. How do we find the invisible? We rely on their profound influence on their surroundings. One of the primary ways we detect black holes is by observing their gravitational influence on nearby objects. Imagine a star orbiting an empty patch of space, or dancing around an invisible partner. If we see a star or a group of stars behaving as if they're orbiting something incredibly massive, but we can't see anything there, a black hole is a prime suspect. For instance, astronomers have meticulously tracked the orbits of stars around the centre of our Milky Way galaxy for decades. Their dizzying speeds and tight paths confirm the presence of an unseen supermassive object. Sagittarius, a star, with a mass equivalent to over 4 million suns, all packed into a region smaller than our solar system. This gravitational sleuthing is a powerful tool. Another key method is detecting the X-ray emissions from accretion disks. As we discussed, the gas and dust swirling into a black hole heat up dramatically, becoming so hot that they emit X-rays. Space telescopes designed to detect these high-energy photons can pinpoint these bright X-ray sources in the sky. If the X-ray source is compact and associated with an invisible massive object, it's a strong indicator of an active black hole. More recently, we've even begun to quote 8 black holes. The incredible gravitational distortions caused by merging black holes send ripples through the very fabric of space-time, known as gravitational waves. These faint whispers of cosmic violence were first directly detected by the LIGO experiment in 2015, opening an entirely new window into observing these extreme phenomena. It's like feeling the cosmic tremors of two giants colliding in the distant universe, from the dramatic death of a massive star to the formation of a space-time vortex, from the chilling stretch of spaghettification to the luminous glow of accretion disks and the powerful blast of relativistic jets. Black holes are truly the universe's most extreme laboratories. They challenge our understanding of gravity, space, and time, pushing the boundaries of what we thought possible. We are still learning so much about them, about their role in galaxy evolution, and about the fundamental physics that governs their mysterious interiors. The journey into their depths is far from over, and with every new discovery, we uncover another layer of the cosmos's profound, breathtaking wonder. What else do you think these cosmic enigmas hold in store for us? We've journeyed through the cosmic birthplaces of black holes, gazed upon their colossal hunger, and even learned how we, from light years away, detect their invisible presence. But what happens when you get close? What truly awaits at that boundary of no return, the event horizon? And what secrets might these cosmic leviathans hold, or perhaps slowly release, as the universe ages? Today we dive deeper into the mind-bending physics that govern these ultimate cosmic traps. Imagine, if you will, standing at the precipice of a waterfall. You can see the churning water, hear its roar, and you know that just beyond a certain point the current will become too strong, pulling you inexorably over the edge. The event horizon of a black hole is far more profound than any waterfall, yet the analogy helps us grasp its essence. It's not a physical surface you crash into. It's a boundary in space-time itself, a point where the fabric of the cosmos is flowing inward so fast, faster than the speed of light, that nothing, not even light, can escape. From our vantage point, safe in the cosmic distance, we observe objects approaching this boundary with a peculiar slowness. Think about it. If you were watching a brave, or foolish, astronaut venture towards a black hole, something truly strange would begin to unfold. As they near the event horizon, their movements would appear to slow down. Their flashlight beam, signaling their progress, would dim and redden, stretching its wavelengths as it fights the black hole's immense gravity to reach us. Time, for them, would seem to be running slower and slower. This phenomenon, known as gravitational time dilation, is a direct prediction of Einstein's general relativity. The stronger the gravity, the slower time ticks, so to us the astronaut would never quite cross the event horizon. They would appear to freeze, forever suspended just above it, their image fading into an eternal twilight as their light becomes infinitely redshifted, eventually vanishing from our sight entirely. But here's the kicker, the truly mind-bending part. For the astronaut themselves, nothing feels out of the ordinary. They continue to experience time at their normal rate. Their watch ticks as it always has. Their heart beats at its usual rhythm. They cross the event horizon without feeling any bump or barrier. It's a smooth, seamless transition from a region where escape is possible to one where it is not. The moment they cross, they look back, and the entire universe they knew shrinks into a tiny, intensely bright sphere above them, eventually winking out of existence as even its light can no longer reach them. From their perspective, their journey continues onward, deeper into the black hole, towards the ultimate mystery. The universe outside simply ceases to be. As our intrepid astronaut plunges further into the black hole, a far more violent fate awaits, one we've briefly touched upon: spaghettification. This isn't just a fun word. It describes a terrifying reality. Imagine the astronaut falling feet first, the gravitational pull on their feet being closer to the black hole's center is significantly stronger than the pull on their head. This difference in gravitational force, these extreme tidal forces, would stretch them like taffy, elongating their body into a long, thin strand of atoms. Simultaneously, the sides of their body would be squeezed inward, compressed by the immense gravity. Their very atoms would be pulled apart, leaving nothing but a stream of subatomic particles spiraling towards the singularity. The intensity of these tidal forces depends on the size of the black hole. For stellar mass black holes, those born from collapsed stars perhaps just a few times the mass of our Sun, the tidal forces become lethal before you even reach the event horizon. You'd be spaghettified long before you crossed the point of no return. A rather unpleasant way to go, wouldn't you agree? But for a supermassive black hole, like Sagittarius A star at the center of our Milky Way galaxy, which boasts millions of solar masses, the event horizon is vast. The gradient of gravity across your body at the event horizon would be much gentler. You could, theoretically, cross the event horizon of a supermassive black hole completely intact, feeling nothing more than a gentle tug. Your spaghettification would occur much, much later, closer to the central singularity, giving you a brief, terrifying glimpse into the heart of darkness before your inevitable demise. And what is at that heart? The singularity. This is where our current understanding of physics truly breaks down. General relativity predicts that all the mass of the black hole is crushed into an infinitely small, infinitely dense point at its center, a point where space-time itself is warped to an infinite degree. But is it truly a point, or is it something else entirely? Something our equations simply can't describe. Here, the laws of physics as we know them, laws that govern everything from the flight of a baseball to the orbit of planets, cease to apply. The singularity represents the ultimate frontier of our knowledge, a place where the need for a unified theory of quantum gravity, a theory that marries the quantum world of the very small with the general relativistic world of the very large, becomes glaringly apparent. It's a profound mystery, a cosmic question mark at the very core of existence. For a long time, black holes were thought to be eternal cosmic prisons, consuming everything and releasing nothing. They were the ultimate no-hair objects, characterized only by their mass, charge, and spin, with no other discernible features. But then, in the 1970s, a brilliant mind named Stephen Hawking revolutionized our understanding. He proposed something truly astonishing. Black holes aren't entirely black. They can in fact glow and slowly evaporate over vast cosmic timescales. This phenomenon is known as Hawking radiation. How does this happen? It's a beautiful dance between gravity and quantum mechanics. The vacuum of space we now understand isn't truly empty. It's a bustling, frothing sea of virtual particle-antiparticle pairs that spontaneously pop into existence, briefly exist, and then annihilate each other. Near the intense gravitational field of the event horizon, a strange thing can occur. If a virtual particle-antiparticle pair pops into existence right at the edge, one particle might fall into the black hole, while its partner escapes into space. Because energy cannot be created or destroyed, the escaping particle carries away a tiny bit of energy from the black hole itself. Over eons, this slow leakage of energy causes the black hole to shrink, eventually evaporating entirely. Think of it like this. The black hole is slowly, quote 10, away its mass in the form of these escaping particles. This means black holes have a temperature, albeit an incredibly low one for stellar mass and supermassive black holes. The smaller the black hole, the higher its temperature, and the faster it evaporates. A black hole with the mass of our Sun would take an unfathomable 10 to the 67th power years to evaporate, a timescale far, far longer than the current age of the universe. But a microscopic black hole, perhaps one formed in the early universe, could evaporate in a fraction of a second in a burst of gamma rays. This groundbreaking concept elegantly links gravity, quantum mechanics, and thermodynamics, opening up entirely new avenues of thought about the universe. However, Hawking radiation introduces yet another profound puzzle, one that continues to baffle physicists: the black hole information paradox. Here's the crux of it. According to quantum mechanics, information can never truly be destroyed. It might be scrambled, transformed, or hidden, but it can always, in principle, be recovered. But if a black hole evaporates via Hawking radiation, and that radiation is purely thermal, meaning it carries no information about what fell into the black hole, then what happens to all the information about the particles and objects that plunged past the event horizon? Does it simply vanish from the universe? Imagine throwing a book into a black hole. The book contains a vast amount of information, the specific arrangement of its atoms, the words printed on its pages, its history. If the black hole then evaporates, and all that's left is random thermal radiation, where did the information about the book go? If it's truly lost, it violates a fundamental principle of quantum mechanics. This paradox is one of the most hotly debated topics in theoretical physics, challenging our deepest assumptions about the nature of reality. Some theories suggest the information is somehow encoded in the Hawking radiation, perhaps in subtle quantum correlations, or that it remains imprinted on the event horizon itself, possibly in a holographic manner. Others propose that our understanding of quantum mechanics or gravity, or both, is incomplete. The search for a solution to the information paradox is pushing the boundaries of physics, forcing us to rethink the very fabric of space-time and the fundamental laws of the cosmos. So, as we explore the terrifying beauty of black holes, we find ourselves not just learning about cosmic objects, but confronting the very limits of human understanding. From the gentle warping of space-time that leads to time dilation, to the violent embrace of spaghettification, to the profound mysteries of the singularity, and finally, to the mind-bending implications of Hawking radiation and the information paradox, black holes are far more than just cosmic vacuum cleaners. They are laboratories of the extreme, places where the universe whispers its deepest secrets, challenging us to expand our minds and forge new tools to comprehend the ultimate nature of reality. The journey into the abyss is, in essence, a journey into ourselves and into the very heart of what it means to question, to explore, and to wonder. The black hole information paradox, friends, isn't just a quirky little puzzle. It's a cosmic bombshell, threatening to unravel the very fabric of our understanding of the universe. Imagine, if you will, a world where information, the precise quantum state of every particle, every atom, every you, could simply vanish. Poof, gone forever. That's what the paradox implies, and it flies directly in the face of one of quantum mechanics' most cherished principles, that information is always conserved. It can be scrambled, transformed, hidden, but never truly destroyed. So, when Stephen Hawking proposed that black holes evaporate, emitting purely thermal radiation that carries no information about what fell in, a profound conflict arose. If a book full of information falls into a black hole, and the black hole eventually evaporates into a featureless cloud of radiation, where did the information from the book go? Did it just cease to exist? If so, then quantum mechanics as we know it is fundamentally incomplete or wrong. And if information is preserved, how does it escape a region from which nothing, not even light, can? This is the ultimate cosmic riddle, a grand challenge that sits at the very frontier of theoretical physics. To even begin to untangle this knot, we need something more than just Einstein's general relativity, which describes gravity on the grand scale of planets and stars, or quantum mechanics, which governs the subatomic realm. We need a unified theory, a grand synthesis that can describe gravity at the quantum level, a theory of quantum gravity. This is the holy grail of modern physics, the elusive framework that could finally reconcile these two titans of 20th century science. Think about it. General relativity tells us that space-time is a flexible fabric, warped by mass and energy. Quantum mechanics tells us that everything, even space-time itself, should ultimately be made of discrete quantized packets. So what does a quote 11 even look like? How does gravity, this smooth, continuous force in Einstein's view, emerge from a foamy, probabilistic quantum substratum, the singularity at the heart of a black hole, where space-time curvature becomes infinite, is precisely where both theories break down, screaming for a quantum gravitational description. It's like trying to describe the behavior of a single water molecule using only the laws of ocean currents. We're missing the microscopic picture. Several ambitious ideas are vying for the title of the theory of everything, each attempting to bridge this chasm. Perhaps the most famous is string theory, which posits that the fundamental constituents of the universe aren't point-like particles, but rather tiny, vibrating one-dimensional. Quote 13. Different vibrational patterns of these strings give rise to different particles, electrons, quarks, photons, and even the graviton, the hypothetical quantum particle of gravity. In this view, the universe is a symphony of vibrating strings, playing out the laws of physics. Another contender, loop quantum gravity, takes a different approach, suggesting that space-time itself is quantized, woven from discrete loops of gravitational fields. It paints a picture of a universe where space isn't continuous, but rather a kind of fine, granular fabric, like a cosmic chainmail. These theories are complex, beautiful, and highly mathematical, pushing the boundaries of human thought. While they are still very much under development and lack definitive experimental verification, they offer tantalizing glimpses into what a quantum theory of gravity might look like, and how it might resolve the paradoxes posed by black holes. Could information be encoded in the quantum foam near the event horizon? Could it escape in a subtle, scrambled form that we haven't yet learned to detect? The answers, we believe, lie in the realm where gravity and quantum mechanics finally embrace. But let's stretch our imaginations even further, beyond the known physics and into the speculative, yet mathematically intriguing realms that black holes hint at. If space-time can be warped and twisted so dramatically, could it also be folded in on itself, creating shortcuts? This brings us to the fascinating, mind-bending concept of wormholes. Imagine our universe as a vast flat sheet. If you want to get from one point to another, you have to traverse the distance across the sheet. But what if you could fold the sheet, bringing two distant points together, and then punch a hole through both layers? That hole would be a wormhole, a theoretical bridge or tunnel through space-time, connecting two distinct regions of the universe, or even two different universes. Mathematically, wormholes, sometimes called Einstein-Rosen bridges, are valid solutions to Einstein's equations of general relativity, much like black holes themselves. They describe a sort of cosmic shortcut, potentially allowing for faster-than-light travel or even time travel by linking distant points in space and time. Picture 2. Quote 17 of a wormhole, each resembling a black hole's event horizon, connected by a throat that tunnels through hyperspace. However, there's a catch, and it's a big one. These theoretical wormholes are incredibly unstable. They would likely collapse faster than anything could traverse them, pinching off into a singularity before a single photon could make the journey. To keep a wormhole open and traversable, you'd need something utterly exotic. Negative energy density, or quote 19. This isn't just matter with negative charge. It's matter that literally warps space-time in the opposite way. Normal matter does, pushing it apart instead of pulling it in. While negative energy is possible in quantum field theory on microscopic scales, like in the Casimir effect, creating enough of it to prop open a macroscopic wormhole remains firmly in the realm of science fiction. Still, the mere possibility that the universe could contain such structures is a testament to the wild beauty of Einstein's equations. And what about the flip side of a black hole? If black holes are cosmic drains, sucking everything in, could there be cosmic fountains spewing matter and light out? Enter the theoretical concept of REM white holes. A white hole is, in essence, the time-reversed version of a black hole. While nothing can escape a black hole once it crosses the event horizon, nothing can enter a white hole. Its boundary, like a one-way valve, allows matter and light to exit but forbids anything from coming in. If you were to peer into a white hole, you might see a torrent of ancient, highly energetic particles and radiation bursting forth from a seemingly empty region of space. Mathematically, white holes are also valid solutions to Einstein's equations. If you simply reverse the direction of time in a black hole solution, you get a white hole. However, unlike black holes, which we have abundant observational evidence for, white holes remain purely theoretical. We have never observed one, nor do we have a clear idea of how one might form naturally in the universe. Black holes are the end state of stellar collapse. There's no known physical process that would lead to the creation of a white hole. Some theories have tried to link them to the Big Bang, suggesting that the initial singularity of our universe might have been a white hole, but this is highly speculative. For now, white holes serve as a fascinating theoretical counterpart, highlighting the symmetries and asymmetries inherent in the laws of physics. Now let's take one final giant leap into the truly speculative. If black holes contain singularities, points of infinite density where space-time breaks down, and if quantum gravity hints at a foamy, granular structure of space-time, could these singularities be more than just points of no return? Could they be gateways? Some incredibly audacious theories propose that black holes might be connected to other universes, or even be the birthplace of new ones. Imagine the singularity not as an end, but as a beginning. As matter gets crushed to unimaginable densities, perhaps it doesn't just cease to exist, but undergoes a phase transition, re-emerging in another region of space-time, or an entirely different universe. This idea sometimes pops up in models of the multiverse, where our universe is just one bubble in an infinite cosmic foam, each bubble potentially born from the collapse of a black hole in another universe. It's a breathtaking thought, isn't it? That the ultimate destroyer, the black hole, could also be the ultimate creator. That the very act of collapse in one universe might trigger the expansion of another. This is pure speculation, of course, far beyond anything we can currently test or observe. But it shows the profound depth of the mysteries that black holes present, pushing our imagination to its very limits and forcing us to question the fundamental nature of reality itself. We stand at the precipice of understanding, armed with powerful telescopes, sophisticated gravitational wave detectors, and the brilliant minds of theoretical physicists. The quest to understand black holes is a quest to understand gravity, quantum mechanics, the origins of the universe, and perhaps even the existence of other universes. We are constantly refining our models, developing new observational techniques, and pushing the boundaries of what's possible to detect. From mapping the shadows of supermassive black holes to listening for the ripples of merging stellar mass giants, every new piece of data is a clue in this grand cosmic detective story. The information paradox, the search for quantum gravity, the allure of wormholes, the enigma of white holes, and the mind-bending possibility of a multiverse. These aren't just abstract concepts. They are the leading edges of human curiosity, the questions that keep scientists up at night, dreaming of the next breakthrough. They remind us that the universe is far stranger, far more complex, and infinitely more wonderful than we can possibly imagine. And as we continue our journey, exploring these cosmic enigmas, we are not just learning about black holes, we are learning about the very essence of existence. The marvel of the cosmos continues to unfold, beckoning us deeper into its profound strangeness, inviting us all to participate in this grand adventure of discovery. We've journeyed through the mind-bending physics of black holes, from their violent birth to their potential role as cosmic gateways. We've grappled with event horizons, singularities, and the profound paradoxes that challenge our very understanding of the universe. But now let's take a moment to truly appreciate what these enigmatic objects represent. They are, without a doubt, the ultimate cosmic laboratories, places where the laws of physics are pushed to their absolute limits, revealing cracks in our theories and hinting at deeper truths. Think about it. Where else in the cosmos can you find such extreme conditions? Gravity so intense it warps time and space beyond recognition, matter compressed to infinite density, and the very fabric of reality tearing itself apart. These aren't just theoretical constructs. They are real, observable phenomena, albeit through their indirect effects. And they are, I believe, our greatest allies in the ongoing quest for a unified theory of everything. How do we use these cosmic labs? We observe them, of course. We look for the ripples they send through space-time, gravitational waves, which are like the seismic tremors of the cosmos, carrying information about the most violent events in the universe. When two black holes merge, they create a space-time disturbance so profound that it allows us to probe the extreme gravity regime predicted by Einstein's general relativity in ways no terrestrial experiment ever could. These waves are our new senses, letting us quote 20 the universe's most dramatic concerts and test the very elasticity of space-time. Each detection refines our understanding, confirming some predictions and opening doors to new questions about the nature of gravity itself. But the real challenge, the true frontier, lies within. What happens inside that singularity? What becomes of the information that falls across the event horizon? The black hole information paradox, which we touched upon, remains one of the most pressing, unresolved issues in theoretical physics. If information is truly lost, it violates a fundamental tenet of quantum mechanics, that information is never truly destroyed, only transformed. This isn't just an academic squabble. It strikes at the heart of how we understand reality. Imagine, if you will, a library. Every book, every word represents information. If you throw a book into a fire, the information isn't lost. It's encoded in the smoke, the ash, the heat. It's incredibly difficult to retrieve, yes, but it's theoretically still there. Now imagine a black hole as a cosmic incinerator, but one that seems to make the information vanish entirely. This is the paradox. Where does the book of information about a star, a planet, or even a stray photon go? One of the most intriguing proposals to resolve this paradox comes from the idea of the holographic principle. This radical concept suggests that all the information contained within a volume of space, like the interior of a black hole, could actually be encoded on its boundary, in this case, the event horizon. It's like imagining a three-dimensional image being fully described by a two-dimensional surface, just as a hologram does. If this is true, then the information isn't lost, it's simply painted onto the event horizon, scrambled and complex but still there. This idea, if proven correct, would fundamentally alter our perception of the universe. It implies that our three-dimensional reality might, in some deep sense, be a projection from a two-dimensional boundary. Your brain might be protesting this, and rightly so. It's incredibly counterintuitive. But it's a testament to how profoundly black holes challenge our common sense and force us to consider possibilities that sound like science fiction. To truly understand what happens at the singularity, and to finally resolve paradoxes like the information loss problem, we need a theory of quantum gravity. General relativity describes gravity on large scales, dictating the dance of planets and galaxies, and the warping of space-time by massive objects like black holes. Quantum mechanics, on the other hand, describes the universe at its smallest scales, the realm of atoms and subatomic particles, where uncertainty reigns supreme. These two pillars of modern physics are incredibly successful in their respective domains, but they break down when we try to combine them, especially in extreme environments like the singularity of a black hole or the very early universe. Think of it like trying to describe an elephant using only a microscope, or a bacterium using only a telescope. Neither tool is appropriate for the task. We need a new framework, a unified theory that can describe gravity in a quantum way. This is where theories like string theory and loop quantum gravity come into play. String theory, for example, posits that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating, one-dimensional, 23 different vibrational patterns of these strings give rise to different particles, including the graviton, the hypothetical quantum particle of gravity. In this view, the singularity might not be an infinitely dense point, but rather a complex quantum fuzzball of these strings, where space-time itself ceases to be smooth and continuous, and instead becomes a frothy quantum foam. Loop quantum gravity, another contender, suggests that space-time itself is not continuous, but is made up of discrete tiny, 24 or 25 of space. It proposes that space and time are granular, like pixels on a screen, rather than an infinitely smooth canvas. In this framework, the singularity might be a region where space-time becomes so tightly woven into these quantum loops that it prevents infinite density, perhaps even bouncing back into a new region of space-time. These theories, while still unproven, offer tantalizing glimpses into what a singularity might truly be. If the singularity isn't an infinitely dense point, but a quantum fuzzball or a region of quantized space-time, then the idea of it being a gateway to another universe becomes less like pure fantasy and more like a theoretical possibility rooted in the mathematics of these new physics. Perhaps the matter and energy that fall into a black hole don't just vanish. They might be recycled, re-emerging in another corner of our universe, or even in an entirely different cosmos. This brings us back to the audacious idea of the multiverse. If black holes are indeed gateways, it suggests a cosmic interconnectedness far beyond our current comprehension. Each singularity could potentially be the 27 of a new universe, a cosmic birth canal where matter and energy are reconfigured into entirely new realities. It's a concept that truly stretches the imagination, suggesting that our universe is just one bubble in an infinite sea of universes, each potentially with different physical laws, constants, and histories. While this remains highly speculative, it's a direct consequence of pushing our understanding of black holes to their very limits. Beyond these mind-bending theoretical implications, black holes play a crucial, if often overlooked, role in the grand cosmic tapestry of our own universe. We've talked about stellar mass black holes, but remember the supermassive black holes that lurk at the hearts of nearly every galaxy, including our own Milky Way. These behemoths, millions or even billions of times the mass of our Sun, are not just passive observers, they are active architects of galactic evolution. Their immense gravity influences the formation and distribution of stars, regulating the growth of their host galaxies. They power quasars, the brightest objects in the universe, by feasting on vast quantities of gas and dust, unleashing powerful jets of energy that can span millions of light years. These jets can either stimulate or suppress star formation, acting as cosmic thermostats that control the temperature and density of gas in their galactic neighborhoods. Without supermassive black holes, galaxies might look very different, perhaps even failing to form the beautiful spiral and elliptical structures we observe. They are both destroyers and creators, driving forces in the universe's ongoing evolution. And what about the cosmic censorship hypothesis? This fascinating idea, proposed by Roger Penrose, suggests that nature abhors a, quote, 20th. It states that every singularity in our universe must be hidden behind an event horizon, shielded from the view of distant observers. Why is this important? Because a naked singularity, uncloaked by an event horizon, would expose a region where the laws of physics completely break down, allowing for unpredictable and potentially catastrophic events that could violate causality itself. It would be a cosmic wildcard, allowing us to send information into the past or create paradoxes that would unravel our understanding of reality. The cosmic censorship hypothesis is, in a way, nature's elegant solution to ensure that the universe remains predictable and orderly, at least to us on the outside. As we conclude our journey into the heart of black holes, I want to leave you with a profound sense of wonder and curiosity. These are not just theoretical constructs. They are real, tangible, gravitationally tangible, objects that force us to confront the deepest mysteries of existence. They are the ultimate challenges to our intellect, demanding new physics, new theories, and new ways of thinking about space, time, matter, and information. The quest to understand black holes is far from over. New gravitational wave observatories, advanced telescopes, and brilliant minds working on quantum gravity theories continue to push the boundaries of our knowledge. We are just beginning to scratch the surface of what these incredible objects can teach us. They remind us that the universe is far stranger, far more complex, and infinitely more beautiful than we can ever fully imagine. So, the next time you look up at the night sky, remember the invisible giants lurking in the darkness. Remember the space-time they warp, the light they trap, and the secrets they hold. And remember that in the heart of these cosmic monsters lies not just destruction, but the very key to unlocking the universe's most profound truths. Our journey with black holes may end here, but the universe's grand story and our relentless pursuit of its secrets continues. Always keep that sense of wonder alive. Welcome back, fellow cosmic explorers. We've journeyed through the astounding physics of black holes, from their violent birth to their mind-bending effects on space and time. We've peered into the heart of their mysteries, grappling with concepts like the event horizon, the singularity, and even the perplexing information paradox. But now, we stand at the very edge of the known universe, looking out into the vast shimmering sea of what we don't yet understand. Think of black holes not just as cosmic vacuum cleaners or destructive monsters, but as the ultimate cosmic laboratories. They aren't just fascinating objects. They are extreme crucibles where the most fundamental laws of our universe are pushed to their absolute breaking point. It's here, in these regions of unfathomable gravity and warped reality, that we find the keys, or at least the challenging riddles, to unlocking the deepest secrets of existence itself. What do black holes ultimately teach us about the universe? This isn't just a question about astrophysics. It's a question about the very fabric of reality, about the nature of information, and about the grand symphony of forces that orchestrate everything we see and experience. We've touched upon the black hole information paradox, a concept that truly keeps physicists up at night. If information about everything that falls into a black hole is seemingly lost forever, vanishing into the singularity, then a core tenet of quantum mechanics is violated. Quantum mechanics, with its strange and wonderful rules, insist that information can never truly be destroyed. It might be scrambled, it might be hidden, but it must persist. This paradox is not just a minor disagreement, it's a fundamental clash between two of our most successful theories: Einstein's general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which governs the subatomic world. This is why black holes are so critically important. They are the battleground, the cosmic arena, where these two titans of physics must finally meet and reconcile. We need a theory of quantum gravity, a unified framework that can describe gravity at the quantum level, to make sense of what happens at the singularity, and to resolve the information paradox. Imagine trying to understand the intricate dance of a ballet, but only having half of the music. General relativity gives us the sweeping, majestic movements of the dancers across the stage of space-time. Quantum mechanics gives us the precise individual steps and twirls of each dancer, the subtle vibrations of their point shoes. But without a unified score, we can't fully appreciate the performance, especially when the dancers are pushed to their limits, as they are near a black hole's singularity. This quest for quantum gravity is one of the most exciting and challenging endeavours in modern physics. We briefly mentioned string theory and loop quantum gravity as leading candidates. Let's delve a little deeper into what these ambitious theories propose and how they attempt to mend the rift between our understanding of the very large and the very small. String theory, in its most elegant form, suggests that the fundamental particles we perceive, electrons, quarks, photons, aren't tiny, point-like objects at all. Instead, they are infinitesimal, one-dimensional vibrating strings. The different ways these strings vibrate, like the different notes on a violin string, give rise to the different particles and forces we observe, including gravity. In this view, a black hole's singularity isn't a point of infinite density. Instead, it might be a complex, tangled fuzzball of vibrating strings, a kind of quantum knot that in some formulations could preserve information. This idea profoundly changes our picture of a black hole's interior, making it less of a destructive void and more of a highly complex, information-rich structure. Then there's loop quantum gravity, which takes a different approach. Instead of unifying forces by describing particles as strings, it attempts to quantize space-time itself. Think of it this way. Just as matter is made of discrete atoms, loop quantum gravity proposes that space and time aren't continuous, smooth fabrics, but are instead composed of tiny, discrete, quote, 30 or quote 31 at the Planck scale, an unimaginably tiny scale where quantum effects of gravity become dominant. Space-time itself is granular, like a finely woven tapestry. This theory suggests that the singularity, rather than being an infinite point, might be a region where space-time becomes incredibly compressed and distorted, but still finite and describable by quantum loops. It might even imply a, quote, 32 rather than a true singularity, hinting at a cyclic universe where black holes could play a role in the creation of new universes. These aren't just abstract mathematical exercises. They are profound attempts to redefine our understanding of reality at its most fundamental level. Black holes, by their very nature, force us to confront these questions. They are the places where our current understanding breaks down, where the known laws of physics cease to apply in a coherent way. And in that breakdown, we find the greatest opportunities for discovery. Consider the notion of wormholes again. While highly speculative, the idea of a shortcut through space-time, a cosmic tunnel connecting two distant points, or even two different universes, is a direct outgrowth of general relativity. Imagine folding a piece of paper and poking a pencil through it. The pencil creates a shortcut between two points that were far apart on the unfolded paper. In the same way, a wormhole could theoretically provide a shortcut through the vast expanse of the cosmos. The catch, as we discussed, is that keeping a wormhole open would require exotic matter with negative energy density, something we haven't observed and aren't sure even exists. But the very possibility, even if purely theoretical, pushes the boundaries of our imagination and our understanding of space-time topology. And what about white holes? These are often described as the time-reverse counterparts of black holes. While nothing can escape a black hole, nothing can enter a white hole. They are theoretical fountains of matter and energy, constantly spewing things out. While no white holes have ever been observed, and many physicists doubt their existence, they emerge naturally from the equations of general relativity. They represent another facet of the extreme physics that black holes invite us to explore, challenging our assumptions about the flow of time and the nature of cosmic objects. These extreme theoretical concepts, born from the study of black holes, often lead us to ponder the existence of a multiverse. If singularities could be gateways, if black holes could lead to new universes, or if the very fabric of space-time is granular and capable of bouncing into new iterations, then our universe might be just one in an infinite tapestry of realities. It's a breathtaking thought, isn't it? The universe we inhabit, with its billions of galaxies and countless stars, could be a single bubble in a vast, frothing cosmic ocean. Black holes, in this grand scheme, might be the cosmic plumbing, connecting these different bubbles or acting as the birthplaces of new ones. The cosmic censorship hypothesis, which suggests that all singularities are always hidden behind an event horizon, is another fascinating piece of this puzzle. If naked singularities not cloaked by an event horizon, were possible, they could potentially allow us to observe regions where the laws of physics break down, potentially leading to violations of causality. The hypothesis, while unproven, is often seen as a protective principle, ensuring that the universe remains predictable and that our understanding of physics isn't fundamentally undermined by these extreme phenomena. It's as if the universe itself has a built-in safety mechanism, shielding us from the most chaotic and unpredictable outcomes. Ultimately, what black holes reveal is the profound interconnectedness of everything. They force us to consider not just gravity, but also quantum mechanics, thermodynamics, and even the nature of information itself. They are the ultimate grand challenge for physics, pushing us towards a deeper, more unified understanding of the cosmos. And this journey of understanding is far from over. New observatories, like the Event Horizon Telescope, are giving us unprecedented glimpses into the immediate vicinity of black holes. Gravitational wave detectors like LIGO and Virgo are listening to the echoes of merging black holes across the universe. providing entirely new ways to study these enigmatic objects. Each new observation, each new theoretical insight, brings us a step closer to resolving the paradoxes and unraveling the mysteries. The ongoing exploration of black holes isn't just about satisfying scientific curiosity, it's about expanding the very limits of human knowledge. It's about understanding our place in a universe that is far stranger and more wonderful than we can often imagine. It reminds us that there is always more to learn, more to discover, and more to dream about. So, as we bring this chapter of our journey to a close, remember that black holes are not just cosmic monsters, they are cosmic teachers. They are the ultimate frontier, the places where physics, philosophy, and imagination collide. They challenge us, they inspire us, and they continually remind us of the boundless marvels that await us in the vast, mysterious expanse of our universe. Keep looking up, keep asking questions, and keep dreaming about the science that lies beyond the event horizon. The universe is waiting for us to explore it. We've journeyed deep into the heart of darkness, peering into the cosmic abyss where gravity reigns supreme and the fabric of space-time warps beyond recognition. We've wrestled with the mind-bending concepts of event horizons, singularities, and spaghettification, and even dared to dream of wormholes and other universes. We've celebrated the triumphs of human ingenuity, from Einstein's elegant equations to the groundbreaking images from the Event Horizon Telescope and the rhythmic whispers captured by LIGO. These are monumental achievements. Yes, incredible milestones in our quest to understand the universe. But here, at the supposed end of our exploration, I want to tell you a secret. We've only just begun. Every answer we uncover about black holes seems to unearth a dozen more questions, each more profound and challenging than the last. It's like climbing a cosmic mountain, only to find that the peak we thought was the summit is merely a foothill to an even grander, more mysterious range. This is the true beauty of science, isn't it? The endless horizon of discovery. Think about it. We've spoken about the singularity, that infinitely dense point where our known laws of physics utterly collapse. We've introduced you to the tantalizing possibilities offered by string theory and loop quantum gravity. Models that attempt to smooth out this catastrophic breakdown, suggesting the singularity might not be an infinite point at all, but rather a fuzz ball of vibrating strings or a granular compressed region of space-time. But these are still theoretical constructs, elegant mathematical frameworks awaiting definitive observational proof. We still don't know what truly lies at the heart of a black hole. Is it a tear in reality, a gateway, or something so utterly alien to our understanding that our brains simply cannot yet conceive of it? The ultimate nature of the singularity remains arguably the greatest unsolved mystery in all of physics. It's the ultimate cosmic quote 38, a place where the universe hides its deepest secrets. And then there's the black hole information paradox. Oh, this one truly keeps physicists up at night. We discussed Hawking radiation, the idea that black holes slowly evaporate by emitting thermal particles. If a black hole eventually vanishes, what happens to all the information, the quantum properties of every atom and particle that fell into it? Quantum mechanics, our best theory for the very small, insists that information can never be truly lost. It can be scrambled, transformed, but never destroyed. General relativity, however, seems to suggest that information is utterly obliterated once it crosses the event horizon. This fundamental clash between our two most successful theories of the universe is not just a minor disagreement. It's a profound crisis at the heart of physics. Imagine a library full of books. If you throw those books into a fire, their information isn't truly lost. It's encoded in the smoke, the ash, the heat. Theoretically recoverable if you had a powerful enough computer. But if you throw them into a black hole and the black hole eventually evaporates, does that information simply vanish from existence? This isn't just a philosophical debate. It has profound implications for the very fabric of reality. Resolving the information paradox is a litmus test for any proposed theory of quantum gravity. Does information somehow escape in the Hawking radiation, perhaps encoded in subtle correlations we don't yet understand? Is it stored on the event horizon itself? Or does it, against all quantum odds, truly disappear, forcing us to rethink the very foundations of quantum mechanics? The universe, it seems, has a delightful way of challenging our most cherished assumptions. Beyond these fundamental theoretical puzzles, there are still enormous observational gaps. Take supermassive black holes, for instance. We know they lurk at the centre of nearly every galaxy, including our own Milky Way Sagittarius A star. We've even taken their picture. But how did they get so incredibly massive, so incredibly fast? We see active galactic nuclei AGN powered by supermassive black holes in the very early universe, just a few 100 million years after the Big Bang. That's hardly enough time for them to grow to billions of solar masses through the slow, steady accretion of gas and dust. This leads to the quote fourth. How do these colossal black holes form their initial quote 41? Do they start as stellar mass black holes that merge and grow rapidly? Or do they form through the direct collapse of massive gas clouds, bypassing the stellar phase entirely, creating, quote, 42, that are already thousands or even hundreds of thousands of times the mass of our Sun? The mechanisms of supermassive black hole formation and growth remain hotly debated, a crucial piece of the cosmic puzzle that influences the evolution of entire galaxies. They are not merely passive residents. They are architects of the cosmos, shaping the destinies of billions of stars. And what about a different kind of black hole altogether? We've discussed stellar mass and supermassive ones, and even hinted at intermediate mass black holes. But there's a theoretical class called primordial black holes. These aren't formed from collapsing stars. Instead, they are hypothesized to have formed in the unimaginably dense and chaotic conditions of the very early universe, moments after the Big Bang. Imagine regions of space-time that were slightly denser than their surroundings, collapsing under their own gravity to form black holes of varying sizes, from microscopic, asteroid-sized objects to those rivaling stellar masses. If primordial black holes exist, they could be incredibly significant. Small ones might have already evaporated via Hawking radiation, but larger ones could still be out there, quietly drifting through the cosmos. Some scientists even speculate that primordial black holes could constitute a significant portion of dark matter, that mysterious invisible substance that makes up about 27% of the universe's mass, and whose nature we still don't understand. Imagine the universe's missing mass could be hidden in a vast cosmic sea of ancient invisible black holes. Detecting them would be a monumental discovery, offering a direct window into the earliest moments of creation and potentially solving one of cosmology's biggest riddles. To tackle these profound questions, we need new tools, new eyes and ears to listen to the universe's deepest whispers. The current generation of observatories, as revolutionary as they are just the beginning. On the gravitational wave front, we are eagerly anticipating the next generation. Imagine. LISA, the Laser Interferometer Space Antenna. A proposed constellation of 3 spacecraft forming a giant triangle, millions of miles apart orbiting the Sun. Unlike ground-based detectors like LIGO, which are sensitive to higher frequency gravitational waves from merging stellar mass black holes, LISA would be sensitive to much lower frequencies. This means it could detect the gravitational waves from the mergers of supermassive black holes, or even the subtle ripples caused by a black hole swallowing a smaller object, giving us unprecedented insights into galactic dynamics and the growth of supermassive black holes. It's like having a cosmic microphone tuned to a different, deeper frequency. On the ground, we're developing the Einstein telescope and Cosmic Explorer, next-generation gravitational wave observatories designed to be vastly more sensitive than current instruments. These will allow us to peer further back in time, detect fainter signals, and create a much more comprehensive map of black hole mergers across the universe. Think of it as upgrading from a simple magnifying glass to a powerful electron microscope for space-time itself. For electromagnetic observations, we're looking forward to advanced X-ray telescopes like Athena, Advanced Telescope for High-Energy Astrophysics, which will allow us to study the superheated accretion disks around black holes with unprecedented detail, revealing more about their feeding habits and the extreme environments near the event horizon. And the Event Horizon Telescope collaboration continues to push the boundaries of imaging, aiming for even sharper pictures of black hole shadows, potentially even capturing the subtle quote 43 quote, a ring of light that has orbited the black hole multiple times before reaching us, a direct fingerprint of space-time distortion. These future observatories aren't just bigger and better versions of what we have. They represent entirely new ways of seeing and listening to the cosmos. They are our probes into the unknown, our hope for unraveling the deepest secrets of black holes and, by extension, the fundamental laws of the universe. As we stand on the precipice of these new frontiers, what does it all mean for us? For our understanding of reality, of time, of information? Black holes force us to confront the limits of our knowledge, to accept that the universe is far stranger, far more complex and far more beautiful than we could ever imagine. They challenge our most fundamental assumptions and push the boundaries of human creativity and intellect. This journey into dreamy science isn't just about absorbing facts, it's about igniting that spark of wonder, that insatiable curiosity that drives all scientific exploration. It's about recognizing that the universe is an endless source of mystery, and that every answer we find is merely an invitation to ask an even better question. Black holes, these cosmic behemoths, are not just destructive forces. They are the ultimate cosmic laboratories, constantly challenging us, forcing us to invent new physics, new mathematics, and new ways of seeing. So, as we conclude our deep dive into these enigmatic objects, remember this. the story of black holes is far from over. It is an ongoing saga, a grand cosmic drama unfolding with every new discovery, every new theory, every new observation. We are living in an extraordinary time, a golden age of black hole physics, where the impossible is becoming observable and the unimaginable is slowly yielding its secrets. The universe whispers its profound truths, and we, with our insatiable curiosity, are just beginning to learn how to listen. Keep asking questions, keep dreaming. The cosmos awaits. We've journeyed through the warped landscapes of space-time, peered into the fiery hearts of accretion disks, and even contemplated the strange dance of time near an event horizon. We've discussed the incredible potential of future observatories, LISA, the Einstein telescope, Cosmic Explorer, and the next generation of X-ray eyes, instruments designed to extend our senses deeper into the cosmic abyss. But what specifically are these titans of technology truly hunting for? What are the ultimate mysteries that black holes still whisper to us? Secrets that defy our most sophisticated theories and challenge the very fabric of our understanding. Let's dive into the profound questions that keep physicists up at night, the cosmic enigmas that black holes present, pushing us to the very edge of our knowledge. The SMBH seed problem, a cosmic growth spurt, think about it. We know supermassive black holes, those cosmic behemoths weighing millions or even billions of times the mass of our Sun, sit at the heart of almost every galaxy, including our own Milky Way. And what's truly astonishing is how quickly they seem to have grown. Observations of distant quasars, the intensely bright active galactic nuclei powered by rapidly accreting SMBHs, show us that these colossal engines were already in full swing just a few 100 million years after the Big Bang. That's like a newborn baby suddenly becoming a world-class athlete in mere minutes. How did they get so big so fast? This, my friends, is what we call the Fjärdequotstefotolvedins, and it's one of the most compelling puzzles in astrophysics. Imagine trying to grow a tree to skyscraper height in a single afternoon. It just doesn't seem right, does it? The traditional pathway for black hole formation is the collapse of a massive star, creating a stellar mass black hole. These seeds would then need to gobble up an astronomical amount of gas and dust and merge with other black holes at an unprecedented rate to reach supermassive status in the early universe. But the universe was still young, still forming. How could there be enough material and enough time for such rapid growth? Physicists and astronomers are exploring several intriguing possibilities. One idea is that these early seeds weren't stellar mass black holes at all, but rather, quote, 47 black holes. Picture immense clouds of primordial hydrogen and helium gas, unpolluted by heavier elements, collapsing directly under their own gravity without first forming stars. If these clouds were massive enough, hundreds of thousands of times the mass of the Sun, they could have bypassed the stellar stage entirely, forming massive black holes almost instantly. This would give them a significant head start, a much larger seed from which to grow. Another fascinating theory involves, quote, 48, quote, in the dense cores of young star clusters. Imagine thousands of stars packed incredibly tightly together like a cosmic mosh pit. In such an environment, stars could repeatedly collide and merge, forming ever more massive stars that would eventually collapse into black holes far larger than those formed from single stars. These larger seeds could then more efficiently attract and accrete surrounding gas, ballooning into supermassive black holes. And then there's the truly mind-bending possibility. Could dark matter have played a role? We know dark matter makes up about 27% of the universe, providing the gravitational scaffolding for galaxies. Perhaps, in the very early universe, dense clumps of dark matter created gravitational potential wells so deep that they could have directly triggered the collapse of ordinary matter into massive black hole seeds. It's an active area of research, and one that connects the visible universe to its invisible counterpart. Future gravitational wave observatories, like LISA, are crucial here. If these direct collapse black holes or runaway stellar collision products formed, they would have merged with other black holes, emitting powerful gravitational waves that could be detected from the early universe. By quote 49 quote for these ancient ripples, we might catch the echoes of the very first supermassive black hole seeds forming and merging, finally solving this cosmic enigma. The next generation of X-ray telescopes will also peer further back in time, seeking out the faint glow of accretion disks around these nascent giants. Primordial black holes and the dark matter enigma. This brings us to another deep mystery, one that touches upon the very composition of our universe, dark matter. We've talked about primordial black holes before, those theoretical black holes that didn't form from collapsing stars, but rather from the extreme density fluctuations in the universe just moments after the Big Bang. They could range in size from microscopic, perhaps even Planck mass, to thousands of solar masses, and while we haven't definitively detected them, the idea that they might exist is incredibly compelling. Now here's where it gets truly exciting. Could these primordial black holes be dark matter? It's a tantalizing thought. Dark matter doesn't interact with light, doesn't emit or absorb radiation, and only interacts gravitationally. Primordial black holes fit that description perfectly. If they were abundant enough and distributed throughout the cosmos, they could provide the missing gravitational pull that holds galaxies together without emitting a single photon. Imagine a vast ocean, and you're trying to figure out what it's made of. You see fish, seaweed, but you also know there's something else, something invisible, providing the bulk of the water's mass. Could it be countless tiny dark pebbles? Primordial black holes could be those pebbles, silently influencing the cosmic currents. Of course, there are constraints. We have to consider how many primordial black holes of a certain mass we could have without violating other observations. For instance, if there were too many small ones, their Hawking radiation would have altered the early universe in ways we don't see. If there were too many intermediate mass ones, they might cause, quote, 50 events, brief brightenings of distant stars as a black hole passes in front of them, more frequently than we observe. Gravitational wave detectors, however, are now able to place constraints on the mergers of primordial black holes of certain masses, offering another window into their possible existence. The search is on. Future gravitational wave observatories will be incredibly sensitive to the mergers of even very small black holes, potentially revealing a population of primordial black holes. And advanced astronomical surveys are constantly looking for microlensing events, refining our understanding of how much of the dark matter could be made of these ancient, invisible cosmic remnants. If we ever find definitive evidence that primordial black holes constitute a significant fraction of dark matter, it would fundamentally rewrite our understanding of the universe's history and composition. It's a quest to find the invisible, using the most profound gravitational disturbances as our guide. The information paradox, a cosmic Gordian knot. We've touched upon the black hole information paradox, that profound conflict between general relativity and quantum mechanics. It's arguably the most vexing problem in theoretical physics today, a cosmic Gordian knot that demands a unified theory of quantum gravity to untangle. Let's really lean into it now. Recall Stephen Hawking's brilliant yet unsettling discovery. Black holes aren't truly black. They emit Hawking radiation, a faint thermal glow that causes them to slowly evaporate. This process means that eventually a black hole will completely vanish. But here's the paradox. Quantum mechanics tells us that information, the complete quantum state of every particle that ever fell in, can never truly be destroyed. It can be scrambled, hidden, transformed, but not obliterated. Yet if a black hole evaporates and simply disappears, taking all that information with it, where does it go? It's like burning a book and having not just the physical book disappear, but also the very ideas, the words, the story it contained vanish from existence entirely. This is a fundamental violation of quantum conservation laws. Imagine you have a specific, unique snowflake. It falls into a black hole. According to classical general relativity, all that matters is its mass, charge, and angular momentum. That's just quote 51. The unique, intricate pattern of that snowflake, it's just quote 52, just seems to be lost forever. But quantum mechanics insists it must be preserved. This isn't just a philosophical debate. It strikes at the heart of how the universe operates. If information can be destroyed, then the universe itself isn't truly predictable or reversible at a fundamental level, shattering decades of quantum understanding. So, what are the leading contenders for resolving this cosmic riddle? One powerful idea comes from string theory, the fuzzball hypothesis. Instead of a singularity at the center, string theory proposes that a black hole is actually a quote 53, a quantum mechanical ball of vibrating strings without a definite boundary. The event horizon isn't a sharp, smooth surface, but rather a fuzzy region where the strings of the infalling matter become part of the fuzzball itself, and their information is encoded in the intricate quantum state of this fuzzball. When Hawking radiation is emitted, it's not just random thermal particles, but rather tiny bits of information carrying strings from the fuzzball's surface, slowly carrying away the encoded data. The information isn't lost, it's just incredibly scrambled and spread out, like a holographic projection. This holographic principle is another key concept, suggesting that all the information about the three-dimensional volume of space-time inside a black hole, or even the universe, can be encoded on a two-dimensional surface, its event horizon. Think of it like a cosmic hologram, where the full reality is projected from a lower dimensional boundary. If the information is truly encoded on the event horizon, then as the black hole evaporates, that information might slowly leak out with the Hawking radiation, albeit in a highly entangled and complex form that we can't easily decipher. Then there are more radical proposals like the firewall hypothesis. This suggests that at the event horizon there's a highly energetic firewall that would instantly incinerate anything that tries to cross it, preventing it from ever reaching the singularity. This would preserve information by never letting it truly enter the black hole's interior, but it also means that general relativity's smooth, gentle crossing of the event horizon would be violated. It's a highly debated idea, highlighting the extreme tension between our current theories. The information paradox is more than just a theoretical squabble. It's a profound call for a complete theory of quantum gravity, a theory that can seamlessly merge Einstein's general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which describes the incredibly small world of particles and forces. Black holes, with their extreme gravity and quantum effects, are the ultimate crucible for forging such a theory. If we can solve the information paradox, we will have taken a giant leap towards understanding the fundamental laws that govern everything. The singularity's true nature and cosmic censorship. And what about the singularity itself? We've called it a point of infinite density, a place where space-time curvature becomes infinite and where our known laws of physics simply break down. But is it truly a point? Or is it something else? Something more complex and quantum mechanical? Our current understanding of general relativity predicts this infinite density, but most physicists believe this is merely a sign that general relativity on its own is incomplete. A theory of quantum gravity would likely resolve the singularity into something finite, perhaps a 5-7-sized region where quantum effects dominate, preventing infinite curvature. This brings us back to the cosmic censorship hypothesis, proposed by Roger Penrose. It states that every singularity formed in a realistic gravitational collapse must always be hidden behind an event horizon. We call these, quote, 58, quote, singularities that are exposed to the universe without the protective veil of an event horizon. If naked singularities existed, they would be truly catastrophic for physics. They would be regions where predictability breaks down completely, where cause and effect could be violated, and where we couldn't predict the future evolution of space-time. It would be cosmic chaos, a universe where the rules could be arbitrarily rewritten at any point. The cosmic censorship hypothesis is not a proven theorem. It's a conjecture, a belief that the universe is fundamentally, quote, 59, quote, to physicists, preventing such chaotic scenarios. Black holes, with their event horizons, thus act as cosmic quarantines, isolating the breakdown of physics at the singularity from the rest of the universe. The ongoing study of black holes, both theoretically and observationally, continues to test this hypothesis. Do naked singularities exist? Or is the universe truly censored, protecting us from the ultimate breakdown of physics? The grand quest, echoes of the deep. These are the profound questions that echo from the depths of black holes. They are not just abstract theoretical musings, they are the frontier of human knowledge, pushing us to develop new physics, new mathematics, and new ways of observing the cosmos. The quest to understand black holes is, in essence, the quest to understand the fundamental nature of space-time, gravity, matter, and information itself. It's about finding the missing pieces of the cosmic puzzle, uniting the disparate theories that describe our universe. Black holes are the ultimate cosmic laboratories, places where the most extreme conditions imaginable force our theories to their breaking points. They are the crucibles in which a unified theory of quantum gravity will likely be forged. Every new observation, every new theoretical breakthrough, brings us closer to unraveling these deepest secrets. And as we continue to explore with our minds and our machines, we are not just studying black holes, we are studying the very limits and possibilities of the universe, and indeed of our own understanding. The journey into the heart of a black hole is far from over. The next chapters of this cosmic story are still being written by brilliant minds across the globe, driven by an insatiable curiosity and a profound sense of wonder. And you, my friends, are now part of that journey, equipped with the knowledge to appreciate the incredible challenges and the breathtaking potential that these enigmatic cosmic titans represent. The universe, in all its mysterious glory, awaits our continued exploration. Welcome back, cosmic explorers. We've journeyed through the astounding physics of black holes, from their birth in stellar collapse to their enigmatic cause. We've grappled with event horizons, spaghettification, and the mind-bending implications of time dilation. We've even peeked into the future of astronomical observation, anticipating the discoveries that will undoubtedly reshape our understanding. But now it's time to truly grasp why. Black holes are so much more than mere cosmic vacuum cleaners. They are, as I often say, the ultimate cosmic laboratories, pushing human knowledge to its absolute limits and revealing the universe's most profound truths. Think about it with me for a moment. What makes a laboratory so valuable? It's a place where we can test the boundaries of our theories, where we can observe phenomena under extreme conditions, and where we can uncover entirely new principles that govern reality. Black holes provide precisely these conditions, but on a scale that dwarfs any terrestrial experiment. They are nature's own extreme physics facilities, operating at pressures, densities, and gravitational forces we can only dream of replicating here on Earth. At the heart of their significance lies the enduring quest for a unified theory of everything. Remember how we discussed the singularity, that point of infinite density where our known laws of physics simply break down. This isn't just a quirky anomaly, it's a giant flashing neon sign in the cosmos, screaming for a new understanding. General relativity, Einstein's magnificent framework for gravity, tells us the singularity exists, but quantum mechanics, the equally successful theory governing the subatomic world, recoils from infinities and demands a different picture. This fundamental clash, this cosmic wrestling match between the two pillars of modern physics, is precisely why black holes are so vital. They are the battleground where general relativity and quantum mechanics meet in their most extreme forms. If we can understand what happens at the singularity, if we can develop a theory that smoothly describes gravity at such scales, then we will have taken a monumental step towards quantum gravity. This isn't just about understanding black holes, it's about understanding the very fabric of reality, from the smallest particles to the largest structures in the universe. It's about finally weaving together the quantum realm and the macroscopic cosmos into a single, elegant tapestry. Imagine your brain trying to reconcile two completely different rulebooks for the same game. One says gravity is a smooth, continuous curve in space-time, like a bowling ball on a rubber sheet. The other says everything is made of discrete, jumpy packets of energy, like individual pixels on a screen. How do you make them both true at the same time, especially when you're looking at something as extreme as the singularity? That's the challenge. and black holes hold the key. Theories like string theory with its vibrating fundamental strings, or loop quantum gravity with its quantized space-time, are our best attempts to bridge this chasm. They propose that perhaps the singularity isn't truly a point of infinite density, but rather a region where space-time itself takes on a new, quantized structure, preventing those troublesome infinities. If we could ever see beyond the event horizon, even theoretically, we might glimpse the true nature of space-time at its most fundamental level. Beyond the singularity, black holes also profoundly challenge our understanding of space-time itself. We've talked about how gravity warps space-time, but a black hole takes this warping to an extreme. It's not just a dent, it's a bottomless pit, a cosmic drain from which nothing escapes. This extreme curvature isn't just an abstract concept, it has tangible implications for the entire universe. It forces us to reconsider the very geometry of our cosmos. Is space-time infinitely pliable? Are there limits to how much it can be stretched and twisted? Black holes provide the ultimate test cases for these questions. By observing the space-time around black holes, the gravitational waves they produce, the way light bends near them, we are directly probing the elasticity and structure of space-time itself, validating or refining Einstein's predictions. Consider the notion of gravitational waves, those ripples in the fabric of space-time like waves on a pond. The most powerful of these waves are generated by the collision and merger of black holes, or black holes and neutron stars. When we detect these events, we're not just confirming Einstein's theory, we're also listening to the universe's most extreme symphony, a direct auditory signal from space-time itself, telling us about its fundamental properties under unimaginable stress. These events are laboratories for general relativity, allowing us to test the theory in ways we never could before, revealing its strengths and perhaps, eventually, its limitations. But black holes aren't just laboratories for fundamental physics, they are also cosmic architects, playing a crucial role in the evolution of the universe on a grand scale. Remember our discussion of supermassive black holes, SMBHs, at the hearts of galaxies. It's not just a coincidence that nearly every large galaxy hosts one. There appears to be a profound symbiotic relationship between the growth of a galaxy and the growth of its central black hole. Think of it like this. The black hole isn't just a passive resident, it's an active participant in shaping its cosmic neighborhood. The energy released from matter falling into an SMBH, forming brilliant accretion disks and launching powerful relativistic jets, can either fuel or stifle star formation in the host galaxy. These jets can heat vast regions of gas, preventing it from cooling and collapsing to form new stars. Conversely, they can also push gas outwards, sweeping it into dense clouds that do collapse and form stars. This complex feedback loop means that SMBHs are not just bystanders, they are dynamic forces influencing the very structure and star-forming activity of the galaxies they inhabit. They are, in a sense, the universe's master sculptors, shaping the cosmic landscape over billions of years. Understanding this intricate dance is key to understanding how galaxies, including our own Milky Way, have evolved from the early universe to the present day. And what about the universe's life cycle? Black holes might hold clues to both its beginning and its ultimate end. The concept of primordial black holes. formed in the extreme conditions of the early universe, is particularly tantalizing. If they exist, they could be a significant component of just dark matter, that mysterious invisible substance that makes up about 27% of the universe's mass and dictates its gravitational structure. Imagine if these tiny ancient black holes, relics from the Big Bang itself, are quietly holding our galaxies together. Detecting them would not only solve the dark matter mystery, but also offer an unprecedented window into the very first moments of creation, when the universe was a chaotic, dense soup of energy. Looking to the far future, the concept of Hawking radiation reminds us that black holes are not eternal. They slowly, painstakingly evaporate over unfathomably long timescales. What does this mean for the information paradox? If black holes eventually disappear, what happens to all the information about the matter they consumed? This question leads us down a rabbit hole of quantum mechanics, information theory, and the very nature of reality. It challenges the fundamental principle that information cannot be truly lost. The resolution of this paradox could require a complete overhaul of our understanding of quantum mechanics or gravity, or perhaps even a radical new perspective on the universe itself. It's a puzzle that keeps theoretical physicists up at night, knowing that its solution could unlock secrets far beyond the event horizon. And then, of course, we have the most speculative frontiers, the ideas that push the boundaries of science fiction into the realm of theoretical possibility. Wormholes, those hypothetical shortcuts through space-time, could be a consequence of extreme space-time curvature, perhaps even linked to black holes themselves, while requiring exotic matter with negative energy density, something we haven't observed. Their mathematical possibility within general relativity continues to fuel our imaginations. Could black holes be gateways, not just to another part of our universe, but to entirely different universes, a vast multiverse? While these ideas remain firmly in the realm of speculation, they remind us that our current understanding is far from complete, and the universe holds wonders we can barely conceive. These are the dreams that inspire the next generation of scientists, the quote 62 that drive discovery. So, as we bring our journey through quote 63 quote to a close, I want to leave you with a profound sense of awe and excitement. Black holes are not just terrifying cosmic monsters. They are the universe's most eloquent teachers. They are the ultimate cosmic laboratories, challenging our assumptions, revealing the interconnectedness of fundamental physics, and pushing us to develop new theories that can encompass the entirety of creation. The quest for understanding them is a testament to the enduring human endeavour, our insatiable curiosity, our drive to explore the unknown, and our relentless pursuit of truth. We are on the precipice of a new era of black hole discovery, with advanced telescopes and gravitational wave detectors promising unprecedented insights. The mysteries we've discussed, quantum gravity, the information paradox, the nature of dark matter, the evolution of galaxies, are not just abstract concepts. They are active areas of research, vibrant fields where brilliant minds are working right now to peel back the layers of cosmic mystery. I hope this journey has ignited your own sense of wonder, that it has shown you that science is not just about facts and figures, but about imagination, exploration, and the thrilling pursuit of the unknown. The universe is a vast, intricate, and astonishing place, and black holes are perhaps its most enigmatic and fascinating inhabitants. They are a constant reminder that there is always more to learn, more to discover, and more to dream about. Thank you for joining me on this incredible voyage into the heart of darkness and light, into the profound strangeness and marvelous beauty of our cosmos. The journey of discovery, my friends, never truly ends.